thanks everyone for joining in our talk today. So we are an IEEE Communication Society special interest group under the umbrella of Technical Committee on Cognitive Networks. Our special interest is in AI and machine learning in security. And we are, so our group is chaired by Professor Subha from Stevens Institute of Technology, and we are vice chairs working with her. Myself, Devashri Roy from UT Arlington, and Moinul from George Mason, and Hanif from Rochester Institute of Technology. So what we do, we have, so a brief introduction about our group. Right now we have a we have a LinkedIn presence, and our members are growing. So far we have 600 members in our group, and we also have on website and other an YouTube channel, which I'm going to share later. But you can research us and send us email with more ideas about different talks and discussions. We are open to that. So far, what activities we have done? We had conducted some virtual seminar series. This was during the time of the pandemic, like I think it was between 2020, 21 the time. So at that point, we were inviting many distinguished faculty members and researchers all over the US and all over the world, actually, to give virtual seminar talks related to our group focus research area. And the recorded talks are available. Feel free to check them out in both our website and also our YouTube channel. So after that, right now, what we are doing for last 1.5 years, we started a new initiative as a Rising Stars symposium series, where we invite the rising stars of the research domain or broader area, so that we give them a practice or platform to practice their job talks. And most of our rising stars, they were at that time job market, and many of them are already placed also at the beginning whom we invited. So this is mainly for focus towards mentoring and creating and fostering opportunity for mentorship and also employment opportunities, hopefully. Yeah, so we tell all our rising stars to keep talk in a job talk format, in a 45 minutes talk, and engage with the audience. So these are our different rising stars from previous years. We had from US, from many different states of US, many different universities of US, and also from outside of US. We had from UK, we had from Turkey, our last rising star. So overall, the logistic of the talk is that we request everyone to be muted on entry and stay muted. But please feel free to type in your question in the chat, in the Q&A. So at the end, we will moderate them at the end of the talk. Yeah, so that's kind of overall, we conduct our talks in such manner. And let me just give a brief introduction about our today's rising star, Dr. Rashid Shalim. So Dr. Shalim is a postdoctoral research associate at Virginia Tech. His research focus is explainable and generable AI for resilient wireless communications, leveraging world models, LLMs, active inference, and geometric machine learning and causal reasoning. He's recipient of several awards. You can see that from my slide, different best paper awards, from a first author award from FIU College of Engineering and Computing, and CCI Innovation Award, Scholar Award. He has authored more than 18 peer-reviewed publications in top venues like IEEE transactions and conferences. So with that, I will stop, and please, I will request Dr. Rashid Shalim to start.
Can you please put on the chat? I missed the link to the website of AIML-SIC. Can you put it in the chat?
Yes,
The
yes.
website?
Yeah, we'll put it in the chat.
Thank you very much.
Okay, thank you so much, Devasri, for the brief introduction. And thanks a lot for inviting me for this exciting session. Um, Let me share my screen first. So can everyone see my screen?
Yes.
Okay, okay. Uh, so just short introduction, like I'm Rashid Salim and I'm a postdoctoral associate. I'm working jointly in Department of EC and Department of Computer Science in Virginia Tech. And my supervisors are Dr. Walid Saad from EC and Dr. Naren Ramakrishnan from uh, Computer Science Department. And the topic of my today's talk is like, is isotropy a good proxy for generalization in time series forecasting with transformers that also include the large language models as well? This work has been accepted for publication in transaction and machine learning research. Uh, so that's why I choose this topic to present. So what's the motivation behind these works? So you all know that the vector representation of embedding inside the transformer-based models, including large language models, are very effective in numerical tasks as well. For our cases like time series forecasting. But the black box nature behind those models, especially in the critical application, including autonomous vehicle, energy, weather, finance, raise concerns. For example, if you consider like autonomous vehicles, and if you have slight mispredictions, that means it's life-threatening. It can collide with other vehicles and the pedestrians. Similarly, it goes to the finance. Slight mistakes in predictions might cause you lose millions or billions of dollars. So to provide prediction reliability, it's necessary to open the black box and try to see what's going on inside rather than blindly rely on those models. Although they are very successful in numerical domains and time series forecasting, but there is a little theoretical understanding like how it works and how it generalizes to different data sets. So that's why the fundamental question arises when or how the hidden representation inside those transformer-based models exhibit some structural properties that enable them to generalize in time series forecasting task. To answer this question, in this work, we try to develop an explanatory tool through a novel analysis of isotropy in the embedding space of transformer-based model. That's the goal of this work. Okay. So assuming like we have a diverse background audience here, I'm just trying to give you a very brief and toy examples to explain our main concept. So embedding, why we are concerned with the embedding? Because it is the cornerstones of AI. Every model, machine learning models we have has those embeddings itself. So I'm giving an example for the transformer models that also includes large language models. So it's a toy example for, you can see like, suppose you have three word tokens like adult, child, and cat, and it has an embedding, that means a representation in contextual embedding space. It's nothing but a vector. So you can see that those vector representation here, adult, child, and cat. Now you put a given example or the input, a kitten. So for our general knowledge, like kitten is more related to the cat. So you are expecting the vector representation should be close to the cat rather than something with adult and child. That's the context behind we have. But if you have a lack of structure, like here, so what you can see, like the cat, adult, kitten, children, every vector representation are very closely related. Now, if you consider the kitten here, the kitten is very close to adult rather than the cat. So there is a chance of mispredictions here. So what we expect from these two diagrams? So we are expecting more structure like this. It's more spreaded things rather than something like every presentation or every meeting is confined to a confined space. That's why we need to study the presentation in the meeting space and how it goes. So our expectation is like it should be more spreaded, more structured one in the embedding space. But do you think like the embedding space looks like this simple? No. So practically, the transformer-based model dimension varies from 64 to 2048, or maybe more. But you cannot visualize it, right? So for the sake of visualizability, so we just project it in the 3D dimension, and this is how it looks like. So this is our embeddings, and we need to study these things. And from this study, we want to explain how is your prediction going on will be. Now, I want to relate the isotropy in this embedding study. So what does this mean? So isotropy refers to a geometric property where vector representation in the embedding spaces are uniformly distributed in all directions. This is another toy examples. For example, the left figure, it's more uniform compared to the right figure. It is more skewed. And if we relate with our examples, I can say that, okay, this is the more high, this is higher isotropy because it is more spreaded. This is lower isotropy because it is skewed. And if we bring our toy examples here, this belongs to intuitively in the high isotropic thing. And our skewed example belongs to low isotropy. So our expectation is like more isotropic representation that is more spreaded so that vectors are spread apart and they're contextually related with each other. There is a definition like what is structures in this case. The structure in the embedding refers to meaningful patterns in model representation, while isotropy means that structure is spread uniformly across all the directions. So this is how the structure and the isotropies are related. They are the complementary term. One complements other. Okay. So our study is basically on time series forecasting and not the word thing. So the time series is a continuous value actually. Then you take the instances of those time steps. That means you discretize this. Then you need to apply some quantization techniques. Different models, different architecture use different quantization techniques. They call it tokenization technique, and you can apply quantization patching. So what you get from this time series, you get a time series tokens similar to the language model. That is why you can apply the time series within your transformer-based model. Otherwise, you cannot directly apply the time series there. But inherently, it is more numerical because ultimately will make the prediction for the continuous domains that relate with the time, actually, not the word. So your embedding itself is more, is related to your time pattern, numerical pattern, rather than the language thing. So what we want to do, we want to make a prediction of L timestamps. That means the future L timestamps using transformer-based model. And you can see that's the probability term. You want to make the prediction of future timestamps based on your past time instance. That's the history you get. But our purpose is to provide a theoretical background. That means how the embeddings is related to the predictions. So if you have a look at this equation, you have a dot products between the embedding of the token, input token, and your past or the contextual representation. That is related to your prediction. So this is how the embeddings is related to your predictions. This dot product of vector representation in embedding space, we called it logit, logit. And there is another very important term is the partition function. That is the sum of all logits you have. And the theoretical model that allows you to give this type of equation is called the log linear model. That is why we adopt this log linear model as an analytical abstraction to study the embedding geometry. So this model is solely for those theoretical study. And if this partition function allows you to normalize this exponential term, and ultimately you will get this equation. In this equation, you have the prediction that is related with your embedding or the representation. And this log linear model abstraction is used in our study by linking isotropy to the partition function. I will explain what is the stability mean here. But the whole idea is we have the embeddings, we have the predictions, and isotropy actually used to study those embeddings. We also have a cross entropy formulation for theoretical studies. that actually reduce the divergence between the ground truth model and your train model. And the numerical downstream does. Sorry to interrupt. Can you see my equation, or it is hidden by this?
Yes, we can see it.
Okay, so the downstream numerical task is nothing but the time series forecasting, and again it is related to the logits. I mean the representation we have, and you can see we have the bias terms and the sigmoid. We use this because to suppress the low confidence logits that contribute minimally to the scale divergence. This is the common practice in all machine learning things. So this is our basic formulation. We have the log linear abstraction, and we do this to include or relate the isotropy and the embeddings to the predictions we have. Now, what is the role of isotropy in transformer for forecasting? Just focus on that. Like, strong performance during training does not necessarily transfer to unseen scenario. That means you trained a model for particular data sets and you test it for different data sets. It's not necessarily like you have a very good performance during training and you still have a good performance in testing. It's not actually, you cannot expect that. And it is a generalization problem. To explain this mismatch, we introduce a framework that links isotropy of hidden representation in a embedding space to the stability of the partition function. I will explain how I mean by that. So we have a theorem in our paper. And if I explain this theory in a very simple term, the representational changes may not change the output unless the structure of the embedding space is preserved. So leaving the log is ineffective for the numeric downstream task. So when you have a new data set, obviously your internal representation will changes, but that doesn't necessarily make your log is useful for the downstream task. And this is called the shift-invariance problem of softmax function. Those who works with the transformer-based model, you know that there's a softmax layer in every transformer, and the representation is generated by those softmax layers. So that's why this shift-invariance problem is related to the softmax, and we are studying the representation. And if you don't have the structure in your representation, then that will make your log ineffective. That means it will not generalize to new data sets. What is the solution? Then one way to prevent shift-invariance problem is to keep the partition function stable. So if you have a look, this is our previous equation. The denominator is the partition function here. And if it is stable, then you will have a stable prediction. That means it is a generalizable. And we relate the isotropy concept with partition function through this equation. So if the partition function is stable, the minimum of Z and the max of Z should be similar because it's a stable. Mean and max are similar. That means the value should be close to 1. If you have 1, that means you have high isotropic representation in your model. And if it is stable, that means your prediction is also the stable. So from this equation, you can say that we have isotropic property in the representation that is making your partition function stable. And if it is stable, then your prediction will be reliable. Moving forward, you can see the title, Study of Isotropy in Hidden Representation. So how we study the isotropy. The empirical question is how can isotropy be quantified? Like how you can measure the isotropy and interpret it in practice, and how does this relate to the forecasting generalization across domains? So this is the second question I want to address here. Motivated by theorem 1, we analyze the structural properties of hidden representations. And the structural properties used here is the effective dimensionality, cluster organization, under the softmax-based abstractions we have. I would like all to draw your attention in this table. So it is effective dimensionality defined here. I will explain later, but this means like D0.8 means 80% of the variations. We use different transformer models and number of layers you see. So for example, D 0.8 equal to 4 means in the first layer of your Kronos T5 models, the first 4 prime dimension actually capture the 80% of variance. So the Kronos T5, the original dimension is 512, but it seems like the effective dimension is top 3 prime dimension. That means the 4 dimension. So although it's 600 and 512 dimension embedding space, but the first 4 prime dimension actually captures 80% of your variance. So if you consider like Kronos bolt, what is the value? 1, just 1 dimension. So previously, in my previous example, what is your expectations? Like it is more spread, more diverse. That means if you have more diverse things, you will get best performance. And if it is confined to a single dimension or very closely related, then it has a bad performance. But the effective dimension is showing you the opposite thing. Okay, even though the Kronos bolt, the first dimension capture 80% of your variance, that means every vector representation is very closely related, closely resided in the embedding space, but still they're performing very well. This is very surprising. And that is why we have to, that actually motivate us to go deeper into the embedding space and study what is going on there. Because our general assumptions and this effective dimensional analysis are conflicting, right? Is it really conflicting? No, it's not actually conflicting. So I'm explaining it in my next slides. So what you can see, there's the role of isotropy. Oh no, this one, the spectral alignment in the generalization in numerical settings. So we have to analyze spectrally of the representation in the contextual embedding space. I talked about we have self-attention layer in the transformer, and you can represent the self-attention with this function G psi, and we use a lemma here where we have a Jacobian matrix. So the Jacobian matrix is the gradient of self-attention. So if you have idea on machine learning and what do you want? Actually, we want to minimize the gradient, right? It has supposed to be 0. If it is a very trained model, your gradient should be 0. So intuitively, we want to minimize this function. That's the lemma we are given by this. That's the lemma is giving these things. We need to minimize this function that includes the probability and the representation there. And the theorem said that we have another term here. This is the key and the query matrices of self-attentions. Those who are familiar with the self-attention layer, they know like there's a query and key matrices there. These terms minimizes the objective, I mean this function, and contains m largest eigenvector of the correlation matrix of the input, where m is the rank of lambda. In other words, the self-attention projects the input time series token onto a low dimensional space defined by the top eigenvector of the correlation matrix of your input. That means whether you have 512 or 2000 something dimensional input, the self-attention layer, when it is trained, ultimately project it in the lower dimension defined by the top eigenvectors of your input. So that is why, we are not actually using all the dimension for the transformer-based model. The transformer self-attention layer ultimately project it within the lower dimension. So our theory and lemma said we need to study the embedding in that lower dimensional space defined by top eigenvectors, not considering all the things, because that actually defined your predictions later. Motivated by this lemma and theorem 2, we project the hidden representation of different models. What you can see here is the Kronos T5, LagLamma, Patch TST, Morai. Kronos T5 and LagLamma are the large language model, and Patch TST and Morai are the transformer-based model. And they have number of different layers, but I'm just showing a single layer here, ultimately the last layer we have. And the takeaway thing is like that. I project only three-dimensional things, that the top three eigenvectors, and it catches 94% variance of your whole data sets. For patch TST, it is capturing 97% things. So even we have only three-dimensional representation here, it captures almost over 90% variance you have here. So we want to calculate the isotropy in that lower dimensional space. And there you can use different metric to calculate the isotropy, and one of the metric is called cosine similarity value. But the thing is, if you directly apply cosine similarity value, there is a problem. And the explanation is the stability of partition functions depends on the balanced inter-token cosine similarity in the contextual embedding space. I talked about the balanced thing, but do you think it's the balanced? It is slightly overlapped or the separated clusteral thing. And the global isotropy can be misleading due to the clusters with large centroid distance dominate the variance. You see the cluster distance dominating the variance. So that means the global calculation of token similarity is not, it is not expecting that will destabilize your partition function. So this suggests we need to have local isotropy calculation. That means you need to have those clustering thing. So we applied k-mean clustering, and then we calculate the isotropy. And this is the equations we have. You can see we can subtract the cluster centroids there. Then we calculate the cosine similarity value between the tokens. And the inter-token cosine similarity values varies from -1 to 1. The cosine similarity value 0 means the strong isotropy. So what is your expectation? The cosine similarity value actually give a numerical metric to the isotropy, and its values vary from -1 to 1. But if it is close to 0, that means high isotropy, and we want that. So we want to have a higher isotropy. That means the cosine similarity value should be close to 0. That will stabilize your partition function. That ensures that your representation has a structure. That ensures that you have a generalizable capability. So I would like to shift our focus to the experimental parts and talks more about those isotropy, cosine similarity, and the metrics we have for the relation. So if you see these two tables, the table 2 showing the number of models we have 5 different models with different architecture. Please remember, every model has different architecture. That means they have different representation because the representation varies based on the architecture you have. Some of them have encoder-decoder transformers, some have vanilla encoder transformer, and so on. Different tokenization techniques all makes different representation in our embedding space. And we use 22 different data sets. Out of them, like 12 data sets from the real domain, includes energy, weather, finance, healthcare, transportation, they're the real data sets. And we also conduct our experience with synthetic data sets. There are 10 data sets by varying different parameters here. This is a very good example of the simulation results you can relate. So our expectation is like the isotropy value should be close to 0. And isotropy is solely calculated from the embedding space. So we just have the representation in the embedding, and we just calculate the isotropy. Just to relate it with the practical outcome, we also calculate NMSE. So that's the error rate you have. And you're expecting to have less error, right? So our claim is that if you have a strong isotropy, then the inter-token cosine similarity value should be 0. That leads to lower NMSE and the vice versa. So if you have a look at each of this figure, for example, the first figure is for Chronos T5, and we have 10 different synthetic data sets. When the isotropic value is very close to 0, you have less NMSE. When your isotropic value is increasing, that means you're having higher NMSE. So that shows, like, indeed, if you have a stronger isotropy or the cosine similarity value close to 0, you have less NMSE. That means your prediction error is less. But when you lose your isotropy, if your isotropy is weak, that means it is far from zero. So this is the origin. If it is far from zero, you will have higher isotropy. We have this experiment for different models, 5 different models, and every models you have the similar pattern. Stronger isotropy, that means lower cosine similarity value close to 0 leads to lower NMSC, and this pattern is similar to all models there. Second experiments we did is like we vary the input context length. Sometimes we have the assumption like if you have more input, we have better performance. Is it really true? First, focus on the right-hand figure. This is the input context length for L equal to 500 for the Kronos T5 model. And the below one is the input context length with 100. So you see, if you change the context length, your representation is also changing. They're not the similar representations. Look at here. Okay, for the linear data sets, if you have less the shorter context length, you are having less NMSC. That is opposite to the higher context length. For seasonality, if you have 500 context length, it's true that you are having more historic information, you have lower NMSC. But for the L equal to 100, you have less historic information, you have higher NMSC. So this is the mixing. So sometimes you get lower NMSC for larger context length, but it is not the universal truth. It all depends how much isotropy it created inside your representation. So when you trained a model, you might think, okay, I think that L equal to 500 context length is good for my model. But if you change the data sets, that might not be the same case. For example, for seasonality, that's the true. Higher length is expected. But if you change the linear data sets, you see your performance deteriorate. That means L equal to 500 is giving you more error than L equal to 100. So without looking any end result, if you just study the isotropy here, you see there's a one-to-one relation. So isotropic value close to 0 have lower NMSC. Isotropic value farther from 0 is leading to higher NMSC. So it's all about the embedding things, and your input representation or input context length will generate the isotropy that ultimately defines whether you will have good performance or not. So by looking at the isotropic thing for different data set, you can say that, okay, which contextual length is good for your model. Similarly, we did an experiment by varying the noise level. We add without noise, and we add variance, noise variance, Gaussian noise variance 0.5 there. And you can also relate the NMSC and the isotropy performance. So you see there is a one-to-one relations there. The similar pattern is observed for the different noise level as well. We also conduct the experiment with real-time datasets, and we took the energy datasets, finance, the nature, health, weather, retail, transport, and for all real-time datasets, we also observed the same pattern. So like isotropy value close to 0 leads to less NMSC, and if it is further from 0, it leads to higher NMSC, and vice versa. That's also applicable to the real-time datasets as well. And we also varies the context length for the real datasets. And this time the length is 144 and 96. And we see the similar pattern. It's not always like you will get best performance for the longer length. Sometimes the 96 things will give you the best good performance, and you can see those things by looking at the isotropic thing here. Since I have 5 more minutes, I can explain one more examples. This is directly related to my wireless communication, so I'm really interested to show it with you. In the transportation, for autonomous vehicle, we use different type of wireless signals. And you can use the time division duplexing there or the frequency division duplexing there. So we took two different data sets. One is TDD data sets as an example, and another one is FDD. The first example is for the time division duplexing data sets, and we use GPT-2 model. And we compare our result with other models that use LSTM, RNN, another transformer or recurrent neural network-based model. And you see that the GPU is giving you the best results for different velocity of the vehicles. We use 6 layers of GPT or the self-attention layer, and these are the representation there. And if you consider the cosine similarity values, we can see that the values are very, 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 very close to zeros. If you zoom in, the values are from 0.02 or 0.05. So that means it is a higher isotropic thing that's actually making your performance best. Now, for the same model, we're giving another data sets. That's the FDD data sets. So this one was our previous results. That is the TDD data set. Now we change the data sets, FDD, and you see the performance deteriorate. The same model, same trained model. And if you consider the cosine similarity value, it is much higher. Previously, we had 0.02. Now it's 0.2, 100 times more. That's actually make your internal representation less structured. That actually destabilize your partition function. That is why you are having bad results here. So the summary is like, it's not always necessary you will have good performance for every data sets. If you have isotropy, if you can calculate the isotropy within the clusters things, that actually shows you why it is performing good and why it is not performing bad. The future question is, if your internal representation is not isotropic, what to do? That's actually the future work. What you can do to improve the internal representation by changing the architecture or other things so that it is really generalizable to all the time series models you have. So that's our actually prime focus. So in future, we want to have a representation that is really strong isotropic for whatever data sets you have in your input. So feel free to read this paper. It is available at this moment in the open review, but it will be available to the TMLR soon. And there we explain everything theoretically as well as experimentally. So we have a couple of theories and lemmas there, and we have a lot of experience. I didn't show all the experience there. So everything is there. You can relate those things here.
So can you please, Rashid, put a link to the paper on the chat?
It's actually my very first slide here.
So maybe we can share it after the Q&A session.
Yes,
the link to the paper.
And you can also send me an email. I can share it with you if you want.
So this paper is the one here is isotropic a good proxy, right?
Yes.
This is the paper.
Yeah.
Okay, good. Thank you very much.
Yeah, you're welcome. If you have any question, you can ask me. I'm done with my presentation, actually.
Thank you. So you can either put your question in the chat or you can unmute yourself and ask directly. So while we are waiting for others, maybe I can start with some questions. So I actually had a couple of questions, but you, throughout your presentation, you answered in or explicitly or implicitly in different ways. But since this is a time series forecasting, and
Yes.
I'm just curious, so I'm new to this field. First, I'm learning a lot from your presentation. It's like the sampling rate, since we are sampling, right? It's time series. So the sampling rate, how does it affect? Have you ever studied, have you seen anything that how sampling rate affects the forecasting results?
We didn't explicitly using the sampling here. So it was already done by all of those models. So the models we used here is a published paper. So we analyzed their things. But coming back to your questions, sampling rate obviously has some implication on the embeddings things, because that actually resembles your continuity in your representation.
Yeah.
And that actually goes through your architecture and create the representation. So ultimately, if you study the representation, that also counts the sampling thing. So I said like the future work is to how we can improve the representation. So maybe the sampling or the quantization could be one of the part where you can work and increase your representation thing or increase the isotropy.
Yeah. Thank you.
Welcome.
Okay. So I have one more question.
Sure.
So this idea of isotropy, there's a body of research that is focused on large language models. So how do you see that this is different for time series forecasting, especially in wireless?
Okay, so for the wireless things, obviously, when we analyze the data, it's a very much more complex because we predict the channel state informations. I didn't show the things like we had a lot of pre-processing before making the tokenization there. So that means you cannot directly input the wireless things. The wireless data needs much more pre-processing to make the time series tokenization things there. So obviously it varies data to data. That's why the architecture actually really matters for study the isotropic thing. So we're studying the representation, but the representation came from those architecture thing. And we have a lot of pre-processing architecture before feeding it to the transformer models. So that means everything counts there. Wireless thing was the most challenging data sets we had to process because it's a multidimensional and really complex data sets. We have channel state information. Yeah.
So we have a question in the chat. Is this work the first that looks into isotropy for generalization, or are there more in other areas?
So there are works only with numerical things, numerical experiments. So there was no theoretical justifications there. So we have a couple of theoretical things there. We have the log linear abstractions. We have lemma 1 plus theory 1, theory 2. Those actually gives you the theoretical background to those isotropic studies. So previously it was only in the numerical sense. So you know about the values and we did the experiments, but there was no explanation. So the main contribution of this paper is to provide those explanations through theoretical studies there.
All right. Maybe I can ask a follow-up question. Okay, so we see another question. Could it be used in other areas besides time series forecasting?
Yeah, could be. But the results we have is solely for the time numerical domain because our representation, the forecasting, all belongs to the numerical thing. That's another area of our future work, like to explore these things on the other sectors, including the text things. But our focus was only on the time series.
Okay. So maybe I can ask one more question just to follow up. So it seems like that it depends a lot on the properties of the data.
Yeah,
So,
true.
and it seems like that this research is going to a direction where maybe we will find more about what kind of architecture or tokenization or
Right.
context length is better suitable to meet the requirement of specific data types, data
Right.
properties, right?
Right.
Okay.
Right.
So far, do you have any, did you find any indication for, generally for wireless, let's say, what kind of architecture, context length or tokenization generally works better than compared to LLMs?
So we found that like the GPT-2 type architecture, decoder-only architecture, suitable more for the GPT, I mean the time series things. But we are not certain enough because we need to apply other models with decoder, encoder only things. Then we can came to the conclusion. The focus of this research just to find the isotropic thing, the representation related to the performance. But we can extend it in a various direction, including the questions you have. These are the good sector to explore by looking at the representation. So far, GPT-2 seems good because it's giving you the best isotropic value so far compared to the other models. But this is, we cannot conclude it because more experimental things is needed there. But out of the 5 models we used, GPT-2 was good for the time series thing. And it is also explain another things like not very large model is enough. I mean, is necessarily needed to have better performance. For your data sets, you can have good performance with a simpler model like GPT-2 only, but you can have GPT-5, right? So it all depends on the representations you have. So GPT-2 is enough for you to giving good representation so far. If you're satisfied with the results, I think you don't need to use unnecessarily extensive large models to train your model.
Makes sense. Thank you. So I do not see any other questions from our audience. So since we are here, we still have a little bit more time. Is there anything else, Rashid, you want to discuss in any slide? The last slide that you discussed actually gave a little bit more perspective into this work.
Yeah. Let me see what I have here. So maybe I can give a conclusion. So
Yes.
I didn't show this figure. I have a couple of times here. So that's the starting point. You have a time series, and you can represent the time series through any equation. We have this equation, so that generates the time series. Then you actually get the observation, but observation is not enough. You need to have tokenized it. Tokenization technique is needed based on your observation. So different architecture use different tokenization technique, maybe the quantization or patching. That will ultimately give you the time series tokens. So from time series, you are generating time series tokens. That actually includes other neural network thing, linear models. So that's the pre-processing parts. I didn't show it here. Our only concerns in this work is to have the self-attention layer. That's the transformer. I wrote LLM, but it's also applicable to any transformer-based model. And every transformer has number of layers. So you can extract the embeddings from each of these layers. So you can study the isotropy for each layers. So this is what we did, but we're ultimately concerned with the very last layer because that actually gives you the logits, because that actually define your predicted output, right? So that logits is goes inside your softmax based predictions given by this equation, the logit divided by the partition function. This is given by the softmax. So every self-addition layer end with the softmax that actually give you the predictions. And we use the log linear model to relate those prediction things with the representation. Then that predicted output will actually forecast it for your time series model. So either you have good predictions for the future time step, or you might have a bad prediction your future time step. And I just splitted this thing to up and down to show that the upper one is the isotropic value inside those transformer model is very close to 0. That's why you are having good results. And the below one, you're not having that good isotropic things that may lead you to the bad performance. So that's the whole story. You're starting from your time series, and it goes through a lot of pre-processing things, and then you go inside the LLM that actually generate the your representation. So if you study the representation, that actually counts everything, every architectural aspect, the data sets, the tokenization, the sampling, everything is manifested in that representation. So it's like a one-time shot. You study the representation, you can actually do a lot of things together. And that representation ultimately gives you the future predictions. And by looking at the isotropy, you can say that, okay, we have good representation or not. Yeah, that's the high level inspiration I have in this backup slide.
Yeah, thank you for the summary. It clearly encompasses everything that you just presented.
Yeah, thank you. Thank you so much.
Thank you. So, so I do not see any other questions from the audience. So we will end our today's talk here. Thank you, Dr. Rashid Shurin, for accepting our invitation. It was great to see your work, and I personally learned a lot. This is a line of research that I have been pondering for some time, and I gained some insights through this research.
It's
Thank
my
you for
pleasure.
that.
Yeah, really great to know that I at least contributes something among the research community.
Thank you, and best of luck for your future wherever you go.
Thank you.
It was nice having you in our
Yeah.
Rising Star Symposium.
Yeah, thank you so much, you and Debusri, for arranging this wonderful event, and I'm really glad to present our work here. And I'm really looking for future collaboration. If you are interested, anyone from the audience can communicate with me and my research group. We're happy to collaborate.
All right. Thank you. Thank you, everyone.
Okay, bye.